Hello, welcome to my talk on understanding Bernoulli's equations. As we know, in mathematics, we can say Bernoulli's equation is an integral form of Euler equation, that is, for inviscid flows. However, for a better understanding of the Bernoulli's equation, we may need to understand what is the physical meaning for Bernoulli's equation. In this talk, we will examine the principle behind the Bernoulli's equations. Bernoulli's equation for general inviscid flow is given as this. And if you want to know how this Bernoulli's equation is derived, please watch my talk on Bernoulli's equations for inviscid flows. Here, V is the velocity, and P is the fluid pressure, and Z is the coordinate in the vertical direction. See this coordinate. Rho is the fluid density, and G is the gravitational acceleration. C0 is the integral constant when we obtain the Bernoulli's equation. In deriving the Bernoulli's equation, we assumed the fluid is inviscid. Thus, the Bernoulli's equation is derived based on Euler equation. The fluid is incompressible, hence the fluid density ρ is a constant. The body force must be conservative, and the most used body force is the fluid gravitational force. It's a conservative force. On the streamline, for instance, in the application, the flow in pipes can be regarded as streamlines or stream tubes. The Bernoulli's equation can be in different form. Here, we'll talk about the Bernoulli's equation for the incompressible irrotational flows. The Bernoulli's equation is given as in this form. The requirement for this Bernoulli's equation include the fluid is inviscid, so this Bernoulli's equation is again derived from Euler equation. The fluid is incompressible, such that the fluid density is constant. The body force is a conservative force. Here, the conservative gravitational force is only included. This Bernoulli's equation is only valid for irrotational flow, for both steady and unsteady flows. So if we apply the definition for the fluid velocity given by this, so the Bernoulli's equation can be written as in this form. So if we compare this equation to the conventional Bernoulli's equation for general inviscid flow, we can see the main difference is the unsteady term given in here. Therefore, the Bernoulli's equation for potential flows would be slightly different from the conventional Bernoulli's equation, including the flow can be unsteady. For instance, for the water wave, and the Bernoulli's equation is correct for the whole flow field for the potential flow. As a simple example, we apply the Bernoulli's equation for two field points, P1 and P2. So we can calculate the fluid velocity V2 at the water outlet. In the analysis, at the point 1, the fluid velocity v1 is 0. And in the coordinate here, z would be h1, and the pressure at the water surface would be P0, the atmospheric pressure. And at the point 2, the velocity v2 is unknown, and the position z2, we can take it as 0. And P2 at the outlet of the water, the pressure is P0, the atmospheric pressure as well. So apply the Bernoulli's equation for P1. We have the integral constant C0 given as this based on the Bernoulli's equation. And this term would be 0 because V1 is 0. So we have the expression for the constant from the point P1. And we can apply the Bernoulli's equation for the point P2. So we have the expression as this. And here, Z2 is 0. So if we put these two expressions together, we have the equation as this. From this, we can derive the expression as this, and the velocity v2 given as this. In the previous slide, we have obtained the fluid velocity v2 for a water height h1 given as this. Here, we will look at a simple example for a falling ball. See this picture. What is the velocity v2 after the ball falls at distance h1? So in this case, we can study the motion, use energy conservation. In the coordinate here, we can see at the higher position, the total energy of the ball is the potential energy because V1 is 0. So the total energy E1 is calculated as mgh1 in this coordinate. And at the lower position, the total energy of the ball is the kinetic energy here because the height z is 0. So the energy is calculated as E2 given by this. So based on the energy conservation, because we assumed there is no friction acting on the ball, it would require this, the total energy at the higher position equaling to the total energy at the lower position. That is the energy conservation. So based on the analysis, we have this expression. So this relation means the potential energy converts to kinetic energy fully. So based on this relation, we can calculate the velocity v2 given by this expression. It is interesting to see for both fluid and solid, when the height is same h1, the corresponding velocity v2 would be same, calculated in the same formula. Now we return to the previous example for the water in the tank. And now we can assume a small fluid element with the volume V, see picture here, and the corresponding fluid mass in this small volume given by m rho V. So if we turn the volume V to the Bernoulli's equation, we can have the equation given as this. Here, C2 is the new constant given in this formula. So if we apply the mass of the fluid element, we have the expression for the transformed Bernoulli's equation given as this. Obviously, the first two terms comprise the conventional mechanical energy as we have seen in solid mechanics, kinetic energy, and the potential energy. However, in the fluid, we have an additional term here. This is the term due to the fluid pressure, and this is a very important term in the fluid dynamics. As such, we can understand the Bernoulli's equation is a conservation form of the specific energies for fluids. And the first term on the left-hand side is the specific kinetic energy. The second term is the specific potential energy. And the third term, we can call it as the elastic potential energy. So all this specific energy together is a constant. That means in fluids, all three specific energy can be converted from one form to another form. And we will see in fluids, the transform of the potential energy and the kinetic energy is via the pressure, the elastic potential energy. Similarly, for the Bernoulli's equation for potential flows, we can turn fluid element volume into the Bernoulli's equation. We have the transformed Bernoulli's equation as this. Here, C3 is a new constant given by this. And if we replace the mass of the fluid element, we have the transformed Bernoulli's equation as this. So again, we can see these two terms are very similar to the kinetic energy and the potential energy in the solid mechanics. But here, we can also see two more terms. One is due to the change of the local velocity, and the other term same as in the previous situation due to the fluid pressure. Therefore, we can see this Bernoulli's equation is again a conservation form of special energies for potential fluid. The first term is the special energy due to the local velocity change. This term is the specific kinetic energy and the specific potential energy given by this, and the specific elastic potential energy due to the pressure. And all these specific energies together make a conservation system. Generally, we have two slightly different Bernoulli's equations. The conventional Bernoulli's equation given in this form, and the Bernoulli's equation for potential flows given in this. The requirements for these two Bernoulli's equations are very similar. They all only valid for inviscid flow, but for the conventional Bernoulli's equation, only steady inviscid flow is valid. And the flow is incompressible, so the density is constant. Compressible flow can be also possible for the Bernoulli's equation, but it would be only useful for high-speed flows. The body force must be conservative, and this is simple because the fluid gravitational force is a conservative force. And for the conventional Bernoulli's equation, it is only valid on the fluid streamline, while under the assumption of rotational flow, the Bernoulli's equation is valid for the entire flow field. Therefore, we can see Bernoulli's equation can be regarded as the energy conservation form. The Bernoulli's equation must be derived based on Euler equation, the governing equation for inviscid flows. Thus, the fluid friction is ignored. Therefore, in Bernoulli's equation, there is no energy dissipation within the fluid. The specific kinetic energy, potential energy, and the specific elastic potential energy due to the fluid pressure can be converted each other in the fluid. But this specific energy together is a constant. That means the energy conservation. Having seen the requirement for Bernoulli's equation, their applications are very wide. We can say Bernoulli's equation can be regarded as the most used equations in the fluid mechanics and the fluid dynamics. The reason for this can be justified as this. In viscid flow, all fluids are viscous, but air and water have very small viscosity. Thus, the inoculants of the viscosity in air and water can be acceptable in many practical applications. In compressible flow, all fluids are compressible, but in small flow speed, the fluid compressibility can be ignored, even for the air, when Mach number is smaller than 0.3 or the air speed is less than 100 meters per second. So many practical applications would be within this range. Conservative body force. The most used fluid gravitational force itself is a conservative force. So there is no particular problem in this assumption. In many practical flows, the main flow field might be far away from the boundaries. In that case, the flow can be regarded as the potential or rotational flows. For instance, for the paper flows, the dominant flow away from the paper wall can be regarded as a potential flow, except in the very thin boundary layer on the paper wall, in which the flow viscous effect may be important. Another example is the flow around an airfoil when at a small angle of attack. The flow is largely the rotational flow, except the very thin boundary layers on the airfoil surfaces.